Welcome to Hart und Trocken. My name is Dirk Schiebon, and in this video I want to demonstrate you tips and tricks and examples of how to find limits of sequences. In our last video we talked about what a sequence is and when a sequence has a limit. In very simple words, a limit of a sequence is a real value which the members of the sequence approach when n tends to infinity. We have talked about rules for limits. That means how we can find limits of sequences which are the result of a combination of simpler sequences. Like this, for instance, the sequence an plus bn is the combination of the simpler sequences an and bn. And if we know the limit of an and bn respectively, which we call a and b, we can find the limit of an plus bn by splitting the sum up and taking the respective limits of an and bn separately, and finally adding these limits up again. And we have similar rules for combined sequences which are created by the multiplication or the division of simpler sequences. Now, based on these rules for limits, we can try to find the limits of sequences which are based on more complex expressions. For instance, let's start with an equals n over n plus 1. In fact, this is a very easy sequence and we can easily write down the first members, which is 1/2, 2/3, 3 over 4, 4 over 5, 5 over 6, and so on. So you see the denominator is always 1 higher than the numerator. It is very obvious that this sequence tends to 1. But we want to find this result in a mathematically exact way. So we keep that as a guiding idea and do some manipulations to that n over n plus 1 expression. Now, one first very important trick is that whenever a sequence is given by a fraction, that both for the numerator and the denominator, n should only occur in the denominator of the respective sums, which occur in the numerator and the denominator. So let me show what I mean. We reduce this fraction by n, so we get n over n, to do it very detailedly, and again n over n plus 1 over n. So I reduce the fraction by n. And of course now we can simplify, which is 1 over 1 plus 1 over n. So now I have that situation which I wanted, because n is only occurring in the denominator of the respective sums, which is here in this denominator. Why do I want to achieve this situation? Well, this sequence taken on its own is a so-called zero sequence. It has the limit 0. So if n goes to infinity, 1 over n tends to 0. So that is a well-known fact which we can use here in our argumentation. Now we apply the rules for limits. So that equation sign is due to the rules for limits. Because now we can split up both the summation in the denominator and the big fraction, that means the division, and look at the limits separately. But the other sequences are very simple. This one can be considered to be the constant 1 sequence, which of course goes to 1. It's only 1, 1, 1, 1, okay? And also this one has the limit 1. So now the rules for limits allows us to split this up to 1 over 1 plus 0. So these blue numbers are the respective limits of these 3 sequences. And finally, as the result, we get 1 over 1, which is 1. So the limit of that original sequence is 1, and that coincides with what we already expected. As a second example, we look at the sequence an equals 5n to the third power plus 4n to the second power plus 5 divided by 2n to the third power plus 8n. Again, the first thing we do here is to put n into the denominator of all these summands. We do this by identifying the summands with the highest power of n. These are those two. Here n occurs in the third power. Next, we reduce the fraction by this highest power of n, in this case n to the third power. So we get the following fraction: 5 plus 4. Now n to the second power divided by n to the third power is 1 over n. So 4 times 1 over n plus 5 times 1 over n to the third power divided by 2 plus 8 times 1 over n to the second power. So now we're ready to apply the rules for limits. So I start with lim for limit n to infinity of an equals, well, now we replace an by the fraction we have just calculated, which is 5 plus 4 times 1 over n plus 5 times 1 over n to the third power divided by 2 plus 8 times 1 over n to the second power. Now, using the rules for limits, we may distribute the lim n to infinity to the different summands in the numerator and the denominator of the fraction. So we get lim. Now I just leave away the n to infinity, okay, because that is taken for granted. So I have lim 5 plus 4 times lim 1 over n plus 5 times lim 1 over n to the third power divided by lim 2 plus 8 times lim 1 over n to the second power. Now, why did we do that? Because we know something about the limits of the sequences where n is still involved. These are these three. So what do we know about these sequences? Well, because n is in the denominator and not in the numerator anymore, all these three sequences are 0 sequences. That means their limit is 0. The remaining two limits, lim 5 and lim 2, are limits of constant sequences. So the limits are very easy. That is 2 and that is 5. So using all these simplifications, we can write 5 plus, well, the remaining summands in the numerator are both 0, so only 5 remains divided by 2. And that's it. That is the limit of our sequence. There we go. So let us note that general rule: if we have an equals 1 over n to the power of k with k greater than 0, then we have that an is a 0 sequence. That means the lim n to infinity of an equals 0. That is a general rule which we used here in this example and in the example before. The next example we look at is the following sequence: an equals square root of n plus 1 minus square root of n. This sequence can be thought of as the difference of two sequences. This is the first one and this is the second one. Let us call the first one bn and the second one cn. Looking at the graphical representation of bn, the orange points, and cn, the blue points, we see the typical shapes of square root functions, which is not surprising because we have the square roots here. So the sequence we are interested in is the difference between bn and cn, and that is represented by the differences of these 2 points, respectively. So the question is this a 0 sequence? Because you can see they approach each other more and more. But that is only a graphical expectation. To know it for sure, we have to prove it with a rigid mathematical approach. So let's do that. Now here we use a little trick. We multiply the formula of the sequence with this expression, square root of n plus 1 and now plus square root of 1. So we multiply the expression by this expression, and of course we have to redo that by again dividing it by this expression. Now let's see why we do that. So that is our original sequence, and we put that into brackets and multiply it with this new expression, which differs only by the sign here. And then we divide it by that expression again. So we write it here, n plus 1 plus square root of n. Now, what should that be good for? The thing is that we can do something with this part. We can apply the third binomial formula. Now let's recall the third binomial formula. It's a plus b times a minus b equals a squared minus b squared. And if we apply that here, we find that we have n plus 1, which is the square of this expression, minus n, which is the square of this expression. And of course we have to divide this by the denominator as above. But now the numerator gets very easy because we have n plus 1 minus n, which is simply 1. So there's only the number 1 remaining. And you see how that simplifies. And we still have the denominator square root n plus 1 plus square root n. So now let's examine this expression in the yellow box more closely. First, it's easy to see that this expression is always greater than or equal to 0. So it never can get negative. Secondly, I want you to compare the expression in the yellow box with this expression. What is the difference? Well, the difference is that we have replaced the square root of n plus 1 by the square root of n. Now, apparently the expression which we used as a replacement is smaller than the expression which has been replaced. That is smaller than square root of n plus 1. So altogether, the denominator is smaller, which is why the expression in the orange box is greater than the expression in the yellow box. If we bring this all together, we have 1 over square root of n plus square root of n, which is the expression in the orange box, is greater than or equal to 1 over square root of n plus 1 plus square root of n, which is the expression in the yellow box, greater or equal 0. Now if we look at the expression in the orange box, that can be simplified to 1 over 2 square root of n. Now where does this sequence go if n tends to infinity? That obviously is a 0 sequence. So that goes to 0 when n goes to infinity. So in mathematics, that is called a squeezing trick, because we squeeze the expression in the yellow box between 0 on the right-hand side and a 0 sequence on the left-hand side. So taking the limits, we have 0 is greater than or equal lim n to infinity of our expression in the yellow box, which we're interested in. So 1 over square root of n plus 1 plus square root of n, and again greater than or equal 0. So you see it's been squeezed between two zeros, so that must also be 0. So the consequence is that the limit of an is 0. And that is in accordance with our expectation. Now let's do another example. An equals 2 times 4 to the power of n plus 5 to the power of n plus 1 divided by 3 times 5 to the power of n plus 7 times 2 to the power of n. So first note that they all are powers of n except for one n plus 1. We can change this to n by splitting away one factor 5, what we do now. So we have 2 times 4 to the power of n plus and now 5 times 5 to the power of n. So that is the change. And 3 times 5 to the power of n plus 7 times 2 to the power of n. So now we only have expressions of some bases to the power of n. Now we choose those of these expressions with the highest basis. This is the basis 5 and we have 2 of them. In the next step, we reduce by this expression. That means we reduce the fraction by 5 to the power of n. So we get 2 times 4 over 5 to the power of n plus 5. Well, in this case, 5 to the power of n cancels entirely out. Divided by 3. Here 5 to the power of n also cancels out. Plus 7 times 2 over 5 to the power of n. So 2 sequences remain where n is involved, which is this one and this one. However, both of these sequences are of the form q to the power of n with absolute value of q strictly smaller than 1. And we already know that the limit of those sequences are always 0. So there are 0 sequences. That means these two tend to 0. Such that in the limit, so I can't write an equation sign, but I can write something like n to infinity. So we get, well, the first summand in the numerator just vanishes because it's a 0 sequence. So 5 remains, and in the denominator, the 3 is remaining, and the other summand is vanishing because it goes to 0. So that is the limit of that sequence. Let's write that in a nice way. So we have lim n to infinity of an equals 5 over 3. So let's look at the next example, which is an equals 1 minus square root of n minus 1 over n divided by 1 minus n minus 1 over n. So what can we do here? Well, the trick is that we can apply the third binomial formula in order to reduce the fraction. Let me show you how that works. For reasons of simplicity, we first replace the expression n minus 1 over n by, let's call it b, with b equals n minus 1 over n. The third binomial formula allows us to split up 1 minus b into 1 minus square root of b times 1 plus square root of b. That is the third binomial formula in this special case. We use this to split up the denominator in this fraction. So we can write is equal to 1 minus square root of b divided by 1 minus square root of b times 1 plus square root of b. In this fraction, the expression 1 minus square root of b occurs in the numerator and in the denominator. So we can reduce the fraction by this expression, which gives 1 over 1 plus square root of b. And if we resubstitute b, we get 1 over 1 plus square root of n minus 1 over n. Now we can start splitting up the limits. So let's write lim n to infinity of an equals lim 1 over lim 1 plus lim square root of n minus 1 over n. Now the only interesting part here is this one. And we need to find out what the limit of that sequence is. So where does the expression under the square root go to? This expression is n minus 1 over n. Where does this go to? Well, we can split that fraction up into n over n minus 1 over n, which is 1 minus 1 over n. 1 over n, however, is a zero sequence, so this goes to 0. So what remains in the limit is, if n goes to infinity, is 1. So if the limit of the sequence under the square root is 1, the limit of the sequence itself is also 1. So we have that this limit is 1. Putting it all together gives 1 over 1 plus 1, which is 1/2. So the limit of an equals 1/2. Admittedly, the trick with the binomial formula is a bit hard to see. So that is a trick one has to keep in mind whenever you come across a similar sequence. Next, we look at the sequence an equals 2n plus minus 1 to the power of n divided by n. This one is comparably simple because we can split up the fraction to, well, 2n over n plus minus 1 to the power of n over n. And of course, the first summand just reduces to 2, which gives us 2 plus minus 1 to the power of n over n. Now the only component in this formula which contains n is this one. And it's fruitful to understand how it behaves. Well, what does the numerator do? It is minus 1 to the power of n. So for n equals 1, we have minus 1. For n equals 2, we have minus 1 times minus 1, which is 1. For n equals 3, we have minus 1 times minus 1 times minus 1, which is minus 1 again. So you see that sequence oscillates between 1 and minus 1 forever. And of course, what happens in the denominator, that is easy, that is 1, 2, 3, 4, and so on. So altogether, we have a sequence which looks like minus 1 over 1, 1 over 2, minus 1 over 3, 1 over 4, minus 1 over 5, and so on. So where does this go to? Well, obviously it goes to 0. So that is a 0 sequence, just as if we didn't have the minus signs. Without the minus signs, the sequence looks like this, just roughly sketched. And with the minus signs, well, the sequence looks like this, and then this jumps down here, and then we go up here, and this one jumps down here, and then we go up here. So you see it moves around the 0 line, but it's still a 0 sequence. So that means that when n goes to infinity, this goes to 0, for n goes to infinity. So altogether, the limit of our sequence is 2. So I can't write equals 2, but I can write goes to 2 for n goes to infinity, or the detailed way is lim n to infinity of an equals 2. And before you get bored, we jump to the next example, which is an equals 2 minus 3n over 1 plus 4n, and we put that into brackets and square this expression. So that is our sequence. Now, how can we treat that? Well, of course, we can resolve the square by multiplying both the numerator with itself and the denominator with itself, and we will get more complicated expressions in the numerator and the denominator. However, a better way is to first ignore the square and calculate the limit of this expression inside of the brackets. And as soon we have this, we apply one of our rules for limits and get the limit for the squared version. So let's see what happens with 2 minus 3n over 1 plus 4n. Again, we don't like n to be in the numerator of the respective summons, so we don't like n to be here. We rather want n to be in the denominator of the respective summons, so that is why we reduce this fraction by n, which is actually n to the first power, and that is the highest power of n. That is the rule of our previous examples. We just reduce the fraction by the highest power of n, which is n in this case. And what do we get? Well, we get 2 over n minus 3 divided by 1 over n plus 4. And following our old scheme, we know that this and this are 0 sequences. So this goes to 0 and this goes to 0. And in the limit, so tending to when n goes to infinity, this tends to minus 3 over 4, which is the limit for the expression within the brackets. Now from our rules for limits, we have lim n to infinity a n equals, well, now lim n to infinity of the expression above with the brackets, so 2 minus 3n over 1 plus 4n squared. And now, because this is a square of two expressions, actually a multiplication of two sequences, we can split up the lim on these two sequences. So lim of the first one, which is actually this expression without the square, times the same expression again. So let's repeat that. We could use the square symbol, but let's just do this for a reason of clarity. But this is already known to us because those two are minus 3 over 4 respectively. So we get minus 3 over 4 squared, which is 9 over 16. And that is the limit of our sequence. Now, before we all get tired, we do the next example, which is an equals 1 plus 2 plus dot 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 plus n divided by n plus 10 times square root of n squared minus n plus 1. Well, that's a mean one, because there are some ingredients which we all have to tackle before we find the limit. So the first thing we should discover is that the so-called little gauss is involved, which is the sum of the first n natural numbers. So if you're not sure what I mean, just watch the video for the little gauss we did earlier. So that sum equals the expression n plus 1 times n over 2. That is what the little gauss is all about. So we replace the numerator by that new blue expression and we get the following. We get n plus 1 times n divided by 2 times n plus 10 times the square root. In the next step, we do all the multiplications, both in the numerator and the denominator. That means we break up the brackets by expanding the multiplications. That means we have n squared plus n in the numerator, and we have 2n times that long square root plus 20, and again the long square root. Now we follow the standard rule we know from our examples before, which is we figure out the highest exponent of n in these summons and reduce by this exponent. So that is n squared. So we reduce the fraction by n squared. That gives 1 plus 1 over n divided by, now we have to be careful with the denominator. So there are two summons in the denominator and we have to divide each summand by n squared. So the first will give 2 times 1 over n, then the long square root, plus 20 times 1 over n squared, then the long square root. Now, what can I do with these two expressions? The idea is to take them under the square roots by first taking the square of them and then taking them into the square root. So first we square both of these expressions. Let me write it like this. We square them and then we multiply them into the expression under the square root. This gives 1 plus 1 over n divided by 2 times. Now, 1 over n is 1 over n squared. So we get n squared divided by n squared minus n divided by n squared plus 1 divided by n squared. That is the first square root. And then we have 20 and n squared. Now we divide by 1 over n squared times 1 over n squared is 1 over n to the fourth power. So that is the quotient we have here. N over n to the fourth power plus 1 over n to the fourth power. That's it. Now in the next step, we of course can simplify many of these terms in here. So we get 1 plus 1 over n divided by 2. Now, the first summand reduces to 1, the second summand reduces to 1 over n, and the third stays as it is, 1 over n squared. That's the first square root. And the second one is plus 20. Now the first reduces to 1 over n squared, the second reduces to 1 over n to the third power, and the third one stays as it is, 1 over n to the fourth power. Now it's time to check what happens if n goes to infinity. What happens? We have a lot of zero sequences here. First one is this one, and there's another one. Here's another one. Here's another one, here's another one, and here's another one. They all go to 0 when n goes to infinity. So let's collect what remains. In the numerator, only the number 1 remains. In the denominator, we have 2 times square root of 1 plus 20 times square root of, everything goes to 0. So square root of 0. So that part is 0. That part, of course, is 1. So, what remains? 1 over 2. That's it. The limit of that complicated sequence is 1/2. Okay, so you're still with me? I have another one, which is an equals n factorial over n plus 1 factorial minus n factorial. Ooh, that one looks very bad. So many factorials. But actually that is not bad at all. We just need to understand what factorial is. Just if you don't recall, 5 factorial is 5 times 4 times 3 times 2 times 1. So actually something very easy. Now the trick here is that we need to understand that we can do something with this n plus 1 factorial. Because the only difference between n factorial and n plus 1 factorial, well, it's just like the only difference between 6 factorial and 5. What is the only difference? Well, it's another 6. The rest is the same. So this is 5 factorial and the only difference is this 6 times 5 factorial. So following this idea, we just can write n faculty over, n plus 1 times n faculty. That is the trick. And now minus n faculty. And now it's obvious that we can reduce this fraction very efficiently. Because we can reduce the fraction by n faculty, which is 1 in the numerator, and n plus 1 minus 1 in the denominator, which results in 1 over n, and that's all. And we know already that 1 over n is something very simple. It's a zero sequence. So if n tends to infinity, we have 0 as the limit. So that was a quick one. So as you are probably asleep by now, let's do a little harder one, which is an, and now 1 plus 2 plus 3, yes, that sounds like the little Gauss again, plus n divided by n plus 2 minus n over 2. Now, as I already said, we have the situation as in one of our previous examples, because this sum here can be calculated using the little Gauss. That means using this formula n times n plus 1 over 2. That is well known by now, and we use this to get the following. I simply replace the sum in the blue box by this formula, and we get n times n plus 1 over 2n plus 2. So mind the 2, which is now in the denominator, which comes from the blue formula. And we still have minus n over 2. Now we take things to the common denominator. That means we keep that first expression, which has in the denominator 2 times n plus 2. And the other summand, the minus n over 2, turns into minus n times n plus 2, because we have to expand the fraction in order to get the common denominator of 2n plus 2. There we go. Now we can simplify the numerator by first expanding the multiplications, which is n squared plus n minus n squared minus 2n over 2 times n plus 2. And that simplifies, well, because these two cancel out and these two give minus n. So we have minus n over 2n plus 4. So by expanding the multiplication in the denominator. Now we apply our standard procedure of identifying the highest power of n and reducing the fraction by this highest power. In this case, it is simply n, which is why we reduce the fraction by n. So we have minus 1 over 2 plus 4 over n. Now, as always, 4 over n is a 0 sequence, and we can write that if n goes to infinity, this all goes to, well, what remains, that is minus 1 over 2, so minus 1/2. Now, for those of you who are still not asleep, we're doing another one. an equals 2 plus 2 to the second power plus 2 to the third power plus ... plus 2 to the nth power divided by 2 to the n plus first power. Well, so many powers of 2. Now, the first thing is, let's train ourselves in using the summation notation. So we replace the numerator by an expression using the summation notation. So that is sum symbol, 2 to the power of I, and now we carefully have to check from where to where I is running. The first summand is 2, which is 2 to the first power, and the last summand is n. So I is running from 1 up to n. And we divide this by 2 to the n plus first power. Now, something should feel familiar about the expression in the blue box, at least if you've recently watched my video about geometric series. In that video about geometric series, we have shown that whenever we have a geometric series which is given by some q to the power of I, where I runs from 0 to n, that we can write this sum as a closed expression, which doesn't use any sum anymore, which is 1 minus q to the power of n plus 1 over 1 minus q. So that is C video on geometric series. But that means we can apply that formula to the numerator. But if we watch very closely, we see that there is a slight difference between the expression in the orange box and the formula for the geometric series. The difference is that the summation index in the expression of the orange box starts at 1, whereas the summation index in the formula for the geometric series starts at 0. So we cannot directly apply the formula for the geometric series to the orange box. However, we could modify the expression in the orange box such that the summation index starts at 0. And of course we have to redo that modification afterwards. So in fact, what do we need to do to start at 0? Well, we have to add the number 1 to that sum, which is nothing else than 2 to the power of 0. And that is the missing thing. So we do the following. This equals sum over, now I starting at 0 to n, 2 to the power of I, and now we have to redo the thing we've changed, and that is we have to subtract the number 1 again. Now we divide this by 2 to the power of n plus 1, and we continue down there. So we replace the expression in the blue box using the formula of the geometric series and get 1 minus 2 to the power of n plus 1 divided by 1 minus 2. And now we have to multiply that with the actual denominator, which is 2 to the power of n plus 1. And we have to subtract 1 over 2 to the power of n plus 1. So you see I have split up this fraction into this part and this part. And in that first part, I have replaced the expression in the blue box using the formula for the geometric series. Now in the next step, we can simplify things a little. 1 over 1 minus 2 to the power of n plus 1. Now divided by, so 1 minus 2 is minus 1. So we can write minus 2 to the power of n plus 1. And now we have this expression, minus 1 over 2 to the power of n plus 1. So except for the minus sign, that has the same denominator. So we can change that minus sign to a plus sign like this. And we have taken everything to the common denominator. So we can further simplify. 1 plus 1 is 2 minus 2 to the power of n plus 1 over minus 2 to the power of n plus 1. So now we reduce by, let's say, by minus 2. We reduce the fraction by minus 2. So we have minus 1, now plus, and now 1 power less than n plus 1, which is n. So only to the power of n, because we have divided 2 to the power of n by 2. It remains 2 to the power of n. And the same in the denominator, we reduce by minus 2, so we have plus 2 to the power of n. Again, we want to create zero sequences. So again, we identify, let's say it's not the highest power of n in this case, but it's generally speaking the summons which grow fastest. So these summons are 2 to the power of n, which we have twice. So we take those and we reduce the fraction by those. And I swap the summons in the numerator, so we get 1 minus 1 over 2 to the power of n, divided by 1. And finally, we are ready for the showdown, because now if n goes to infinity, we have that this sequence is a zero sequence. So it goes to 0, which gives us finally the limit 1 for this rather complex sequence. Now, for those of you who made it until this point, I have some very bad news for you, because I have only one example left. And this is the following. an equals 1 plus 1/3 plus 1 over 9 plus ... plus 1 over 3 to the power of n, divided by something which is very similar, but only 5 instead of 3, so 1 over 5 plus 1 over 25 plus ... plus 1 over 5 to the power of n. What is the limit of that sequence? Again, as you very carefully paid attention in my video on geometric series, you know that both the numerator and the denominator are geometric series. A geometric series has the general form I equals 0 to n of q to the power of I equals 1 minus q to the power of n plus 1 over 1 minus q. And for the special case that the absolute value of q is strictly smaller than 1, we have some nice formula for the limit of that sequence. So we can write lim n to infinity I equals 0 to n q to the power of I. Well, that was 1 over 1 minus q. So that is the story about geometric series. And we can apply that here, because 1/3 and 1/5 are both numbers whose absolute values are strictly smaller than 1. So we can calculate the limits for both the numerator and the denominator by using this formula. So I can write lim an, for n goes to infinity, is equal to lim of, well, let's write it like this, n to infinity I equals 0 to n 1/3 to the power of I, just using summation notation to in fact make things easier in this moment, and divided by structurally the same thing, lim n to infinity sum over I equals 0 to n, now 1/3 replaced by 1/5 to the power of I. Now in both cases, the numerator and the denominator, we can use that orange box over here in order to write that in a much simpler way, because that is, well, 1 over 1 minus q, but q in this case is 1/3, so 1 minus 1/3. Now that looks like a double whopper divided by, and the same thing is in the denominator, so 1 over 1 minus 1/5 in this case. Now we have to resolve that double whopper. which is not hard because 1 minus 1/3 is 2/3. So we have 1 over 2/3 over 1 over 4/5. That is funny, isn't it? And that equals, well, 3 over 2 over 5 over 4. And that equals 3 over 2 times 4 over 5. Now we can reduce by 2, which is 3 times 2 over 5. And that is 6 over 5. There we go. That is the limit of that funny sequence. So, well, those of you who made it until here, I am very happy that you followed me on that journey. Actually, producing that video took me 2 days. So that's the end of 2 days work, and I'm really relieved that I did it. So all remains is to say thanks a lot for watching that, and see you next time.